So I was like, not really my thing. But okay, so it is the first day of the rest of your lives, and we're on chapter 3, steady state circuit analysis. And I figured out how to put emojis in my notes, but they don't show up in these notes, but I'm excited about that fact. So look for them in the future. So let's review the bidding. We started out with the fundamentals. We did some really basic circuit analysis just based on the laws that we knew, right? We knew how to do like Ohm's law and Kirchhoff's current law and voltage law, etc. And then we were like, well, let's introduce some new elements, the capacitor, the inductor, and then let's do some real circuit analysis a little bit more systematically. We'll go through a process, set up our equations, including differential equations. When we introduced the capacitor and the inductor, those came in. And then let's solve them systematically for outputs given certain inputs. And so we've done that, and we're feeling, varying degrees of confidence in that material. But one of the things that we sort of bumped up against in the last example that we did is that the steady state response is pretty easily, it is, for a sinusoidal input, merely a change in the amplitude of that sine wave and the phase of the sine wave. So if you put in a sine wave, you get out a sine wave at the same frequency for a linear system, and the only things that change are the amplitude and the phase. And so we're kind of taking that insight, and I'm going to posit that if we just care about the steady state, we don't have to go through the differential equation solution. All we need to do is think about things in terms of impedance, and that's what we're going to introduce here. So this is a sort of shortcut to the steady state solution, which is what we often care about for an electronic system with a sinusoidal input. Sinusoidal input, like an AC power outlet, is going to provide at 60 hertz. So these sinusoidal inputs, often we care about the steady state because the transient response for a lot of these circuits is over very quickly. Microseconds, sometimes milliseconds. So it's very useful to think about it in terms of just steady state. And it's important to note that impedance methods do not give information about the transient response. So if you want to know, like, given some initial condition, what happens with the circuit, you can't find that information from this analysis. So we lose something, but what we gain is that we don't have to go through as complex of an analysis or complicated of an analysis. Complex is the wrong term to use there because we're going to swap out differential equations for complex numbers. And some of you will find that as challenging or more challenging than dealing with the differential equations. So it's like sort of a law of what do they call it? Conserved difficulty, something like that. We're going to go around the differential equation, but we're going to pick up having to use complex numbers, which isn't that bad, but it's just something that is sometimes tricky for people. So we're going to start off with the first lecture on complex or phasor representations of voltage and current. So this is what the EE people have been whining about, if you know any of them, all these years, is phasors. That's your cue to be scared. Phasors, everybody always talks about them like they're so scary, but they're really not. I think that most of it is some confusion around imprecise descriptions, and so I'll try to dispel some of that in this lecture, but we'll see how that goes. I don't know. But I think this is a great lecture. So it is common to represent voltage and current in circuits as complex exponentials, especially when they are sinusoidal. Euler's formula is our bridge back and forth from trigonometric form with cosines and sines to and from exponential form, which is this e to the j theta. So this is Euler's formula, e to the j theta equals cosine theta plus j sine theta. And j in all of this, it's important to note, is the square root of -1, the imaginary number. We use that. We talked about it before, but we use it instead of I because I is for current in this class mostly, but I also use J for an index too. So like, even in the second lecture today, I realized I used J. It was like I could have used K. I should have used K, but I was summing over K.
Could have just done like a fancy I.
Yeah, I probably could have done a fancy I. Used iota.
Or I hat.
I hat.
Or just some random
Or
symbol.
I theta.
Well, J is really common in electrical engineering, and so we're going to use J.
Could use I theta.
So, this is considered by some people to be like the most beautiful formula ever. It is really interesting, and I know a girl who has this tattooed to her palm.
Really?
Yeah, like legit. Like her whole palm is a complex plane representation of it with the equation. She's pretty intense. She's pretty hardcore.
So if I get that
She
tattoo
likes
to my
my
palm, is that excluded from the exam?
Yeah, that's fine. Yeah, you can bring
I
it
heard
in.
that you can exclude them if they do have it tatted on there.
If you're gonna go that far, I think that's cool. Yeah. Just like tattoo your note sheets on your arms.
You deserve it if you do it.
Yeah.
Temporary tattoos.
No, I know someone. Well, I met a person who's like, yeah, I do tattooing on the side, sort of like as a hobby, and he has really cool tattoos than myself. And I'm like, well, that's pretty awesome. He's like, yeah, if you ever have like a party or something, and you want me to just come. So, you know, I'm like, oh my god,
So
unplanned tattoo party? How awesome would that be?
I've seen it so many times.
Oh, that would be great. I think I would have so much fun. The only rule is you can't have planned this tattoo before you can.
Oh, you guys are intentionally doing it.
Okay, so here are a few useful identities implied by Euler's formula. If you make theta negative theta, it's e to the negative j theta. If you substitute negative theta in over here, cosine of negative theta is just cosine of theta because it's an even function, right? And sine of negative theta is just negative sine theta because it's an odd function. And so you have this expression. So I just derived that in words. Would you like that? Okay. All right. This, I get way too much kick out of myself. My wife is like really used to just me just joking and then laughing at myself, and she never laughs. It's pretty good. So cosine theta, we can say is just the real part of e to the j theta. Now, we see that from this, right? This is the real part. And this is the imaginary part. Now, a little note on notation here. In the printed stuff, I'll use this notation where it uses that fractor font, which is really cool, which would work well for tats. But it doesn't, it's really hard for me to write that on a board. I really don't think it's very effective. So, wow, that's not bad. That took a long time though. So I'm not going to try that. So what I'm going to use is the other common notation, which is RE. And for the imaginary part, instead of doing the fractor version, I'll use IM. And what this means is it just takes, it's a function that you input a complex number, and it spits out, if it's this one here, it spits out the real part. If it's this one here, it spits out the imaginary part. So that's that. These are just weird, strange things, but you guys in your notes, that's not like that. I don't know why. When I import that into Illustrator, it comes out weird. But in any case, you can express cosine and sine in terms of real and imaginary parts of e to the j theta, and also in terms of sums of complex exponentials. So these are nice identities to have around, so I just stuck them here so that you have access to them anytime you want. So these equations can be considered to be describing a vector in the complex plane, which is illustrated in the figure. So the complex plane is just the plane made up of the real part of a complex number on one axis and the imaginary part on the other axis. Typically, it's traditional to use the real axis as the horizontal axis and then the imaginary axis as the vertical axis. The real part of a number, so e to the j theta, the real part is cosine theta, just like we saw up here, cosine theta. The imaginary part is sine theta. And if you guys are keeping score at home, sine squared theta plus cosine squared theta is something we would want to do if we were Pythagoras, right? We would want to know what the length of this is, and it would be the square root of that. What is sine squared theta plus cosine squared theta? 1 equals 1. So the length of this is a unit vector, e to the j theta is. We could scale it, of course, multiply it by 17. It's the only thing you can multiply it by, though. Yeah. Good. So that's the complex plane. That's e to the j theta. That's how it's related to this trigonometric form.
The fourth dimension.
Sorry?
Gate to the fourth dimension.
Gate to the fourth dimension. It might be. It's possible. I'll tell you what. If you showed up with a tattoo of it to anything, you're getting it. So it's the gate into every place you go, I'm pretty sure. So if you showed up to the fourth dimension and you had it tattooed on your hand, they'd be like, all right, you're cool enough. You can come
Well,
in.
plus if I'm getting into the fourth dimension, I think it might be pretty hard for them to get me back out.
Yeah, well then, I don't
Get
know.
me out.
Tattoo removal, maybe it's possible, I don't know. So, consider, now, so we just did like the math side, right? We just did like, oh, this is trigonometric form of something that's related to this cosine and sine, complex plane. No idea how this is related to voltage and current and stuff. So let's talk about that. So consider a sinusoidal voltage signal, V of t, is equal to the sinusoid. We're going to use cosine here just for fun. Cosine omega t plus phi. So it has some amplitude, V naught, so V0, and then some frequency, angular frequency omega, and some phase phi. Okay? So that is a sinusoidal voltage, something that we care quite a bit about. We encountered in lecture 2.4 the fact that for a linear system with a sinusoidal input in steady state, the output is a sinusoid at the same frequency as the input. The only aspects of the sinusoid that the system changed from input to output were its magnitude or amplitude and phase. Okay? Therefore, these are the two quantities of interest in a steady state circuit analysis. Our notation simply ignores the frequency omega and represents V of t as V0, 0 e to the j phi. Okay? We call this the complex or Phasor form of v of t. It's also called the polar form. It's like 15 different names for these things. So this Phasor form of the voltage is meant to be shorthand notation, and if interpreted literally can cause confusion. In fact, mathematically, based on how we defined it, v of t is equal to, if we looked back over here, we said, oh, cosine is the real part of e to the j theta. What that would imply is that v of t from the cosine form right here should be written v naught times the real part of e to the j omega t plus phi, right? Which we could rewrite again as being the real part of, and then we can split this into e to the j omega t, e to the j phi, right? So that is really mathematically what v of t is equivalent to. Technically, we can use this more complicated form in our analysis, but we won't because, conveniently, if we just treat the signal as if it was equal to v naught e to the j phi, like we set up here when we defined our Phasor form, and at the end apply our implied e to the j omega t term and this real part, this real function, to the result, everything just works. And trust me, I'm a doctor. Oh wait, I lied. There is an emoji in this lecture.
Thanks for that.
What?
And it showed up in the notes.
Nice. So, yes. The important takeaway is that now I can do emojis, but the second most important takeaway is that we can just treat it like this, and at the end we'll apply this real part and the omega e to j omega t part at the end of our analysis. And lest that sound really confusing, I made a little diagram that should help us navigate it, okay? So, say you have some trigonometric form of your sinusoidal input, okay? Just like we started off with, v naught cosine omega t plus phi. Phase it, in other words, turn it into a Phasor form. You just take the amplitude, and you take the phase, and you just stick them in there like that. Easy enough, right? Just essentially take those, the amplitude and phase, and put them in v naught e to the j phi. Then, operate on it with your circuit. We're going to learn how the circuit operates on these things soon, but we are, for now, we'll just say it operates on them, and it ends up changing the magnitude and phase, right? In steady state, that's all that happens. That's all that matters. If sinusoidal input, we get a sinusoidal output with the magnitude change and the phase change, right? So I'm using prime here to mean it's a new one, not to mean derivative. I don't use prime for derivative in this class at all. So if you see a prime, it doesn't mean derivative. Okay, so we have a new voltage in this form, Phasor form. Now, technically, we should insert this into this expression here to convert back to trigonometric form, which is we should take the real part of e to the j omega t times v naught prime times e to the j phi prime, which, I mean, it looks harder than it really is. Essentially, all you have to do is stick the v naught prime up here as your amplitude of your cosine, and then take your phi prime and stick it up here. And so all that changed in all this is that the v naught turned into v naught prime and the phi turned into phi prime. when we're working with it down here, this form is a lot easier to work with mathematically, and we'll talk about how to use it. So this is my nice little commutative diagram using the maths. Okay. The same process can be used to convert a sinusoidal current to and from phasor form. So this is, we did it all with voltage, but we could do the same thing with current. It's exactly the same mathematical description. An alternative notation for a phasor, V naught e to the j phi, is V naught angle, is this symbol, angle phi. You'll also see it V naught with the angle thing that's extended and the phi is on top. So that form is also used. You'll see it show up if you like Google what the hell are phasors after this lecture. And you're going to see this, and it's in my view, the exponential form is superior. Not because I actually think this is simpler to write, right? Like it's just the magnitude and the phase that you keep it around. But you have to remember how mathematically to combine these things when we start multiplying them by each other and dividing them and adding them. You have to remember like how to do that with this form. When you're in this form, you are already in a mathematical form that keeps track of things for you. So when you multiply these things together, the magnitudes are going to multiply, and then the phases are going to add, right? Because it's an exponential. So e to the j phi, so like for instance, e to the j phi times e to the j psi equals e to the j phi plus psi. Nice. In this form, you would have to remember that you add the phases and you multiply the amplitudes. In the exponential form, it's just follow the math rules that you already know and love, or at least like. Okay. That's all I've got for phasor notation on for sines and for sinusoidal voltage and current. Any questions before we move on to the other lecture?
Question.
Yeah.
Do you watch Doctor Who?
I don't.
Boy,
You know why?
pretty good.
Because I have a finite length of time in my life. And I was like, everybody's like, oh, you should watch Doctor Who. It's really great. And I'm like, oh, okay, like I could get into that. What do you need to do? Watch like 30 years worth of television in order to catch up. Like, what? I don't have time for that.
Yeah, just start with the new ones.
Yeah.
Can
Don't
you?
worry about the old ones.
No, it doesn't matter.
It doesn't matter?
Not at all.
It doesn't really matter. You can watch them forwards, you can watch them backwards. And
Okay.
Start it though, you're not gonna stop.
Is it good?
it's
pretty good.
really good.
It's a
Okay.
little cheesy sometimes. It can definitely be cheesy, but
Okay.
It's got some also good comedy in it too.
Okay. Maybe I'll have to do that. Because I was like, I was like, it seems like a show I would like. People who like it, like I tend to like the same things that they like, but I'm like, you guys, I can't do this. Like this is too much time. Yes, if like I don't know.
you gotta watch it.
If something happens where like society ends, but I can still watch television, maybe I'll catch up. But but yeah, maybe I'll just have to start with where we're at. That's a good steer. Okay.